And I'll start. Seismic waves. Seismic waves travel through Earth whenever the ground is disturbed, whether by natural processes like earthquakes and volcanic eruptions, or by human-made activities such as controlled explosions. Even though these subtle tremors are far too small for us to feel, they carry a wealth of information about the planet's interior layers and the behavior of engineered structures under dynamic stress. At the heart of most seismic and vibration monitoring systems are a device called geophones, which are electromechanical sensors that translate tiny ground motions into electrical voltages. When deployed in arrays, geophones record either ground velocity or acceleration, enabling us to image subsurface geology for oil and mineral exploration, and to detect seismic events in real time. In civil infrastructure, those same arrays or individual units are used in structural health monitoring, where shifts in the buildings or bridges' resonant frequencies can signal damage or degradation. A traditional moving coil geophone consists of a proof mass suspended by springs inside a magnetic field, as seen in the diagram. As the ground moves the outer housing, inertia causes the mass to lag, inducing relative motion between the coil and the magnet. By Faraday's law, that motion generates a voltage proportional to the mass's velocity. So above the sensor's natural baseline frequency, the output is essentially flat in velocity. Hence, geophones act as a band-pass velocity meter. However, typical coil designs resonate between 4 and 14 Hz, and below that resonant peak, their sensitivity decays sharply, a phenomenon known as low-frequency roll-off. This makes it challenging to capture signals below the natural frequency, where many important structural or long-period seismic events actually occur. To push into those lower frequencies and achieve broader bandwidth, researchers have developed fiber optic geophones which use fiber Bragg's gratings or Fabry-Perot cavities to measure motions via optical interference, and microelectromechanical system geophones which shrink the mass spring into systems of silicon chips and can deliver flat responses from direct current up to several hundred hertz. While these technologies offer impressive performance, accurately modeling any geophone response remains non-trivial because real sensors exhibit frequency-dependent damping, mechanical nonlinearities, and electromagnetic coupling effects. Historically, engineering models simplify geophones as linear second-order systems, but even that, specialized circuit analogies, digital correction filters, and sensor fusion algorithms are required to improve low-frequency responses. For example, one source developed a SPICE-based equivalent circuit for a GS1 geophone and achieved amplitude predictions within 8% of the manufacturer's specs. Other studies apply inverse filtering digitally to extend usable bandwidth. Our studies build on this body of work by using modern Python toolkits to replicate published resonance frequencies and spectral characteristics. By combining mechanical transfer functions, instrument response filters, and circuit models, we aim to predict geophone behavior under any seismic input and validate our results against other published calibration data. Next. You're on mute.
Okay, so at the heart of every geophone lies a simple yet powerful mechanism, a small mass suspended on springs surrounded by magnets. When the Earth moves, the housing shifts with the ground, but the suspended mass resists that motion due to inertia. This creates a relative displacement between variables xr and xg, between the sensor mass and the ground. We capture that dynamic with a second-order differential equation in equation 1, shown over there, where m is the moving mass, k is the spring stiffness, c is the damping coefficient, and xr is the mass displacement, and xg is the ground displacement. So from this equation, two fundamental sensor characteristics emerge. So see equation 2 for the damping ratio and equation 3 for the natural angular frequency. These parameters feed directly into the transfer function equation 4. This describes how ground velocity is converted into an output voltage. So in practical terms, the natural frequency defines where the sensor peaks. So typically around 4 to 14 hertz for coil geophones, while the damping ratio, which is defined by the unit zeta, shapes the sharpness of that peak. So a higher zeta unit flattens the resonance, and a lower zeta unit produces a pronounced spike. So most manufacturers aim for zeta approximately equal to 0.7, which balances the sensitivity and stability. So we also consider the quality factor and the sensitivity, which for an SM6 geophone is about 28.8 volts per meter per second. So above that resonant frequency, the coil moves a little and the output closely follows ground velocity. And below the baseline frequency, the sensitivity falls off sharply, so it rolls off at roughly F inverse squared in displacement, or 1 divided by that frequency and acceleration. So following that, regarding advanced sensor technologies, to extend bandwidth and capture lower frequencies, advanced technologies have emerged, such as fiber Bragg grating geophones, FBG geophones for short, replace coils with optical fibers. And so this achieves dynamic ranges around 94 decibels over 10 to 200 hertz. So MEMS geophones miniaturize the mass spring system on silicon. So that offers flat responses from direct current to several hundred hertz and noise floors near 10 to the 9 G per root hertz. So force balanced accelerometers use active control to remain flat down to 0 hertz. So though they tend to be larger and more complex, in summary, whether coil type, optical, or MEMS, every geophone relies on the interplay of mass, spring, and damping to kind of sense ground motion. So these principles form the blueprint for our computation model, which explicitly simulates the second order mechanical response and incorporates the sensor's electrical behavior to predict real world performance. So following that, so we developed a structured Python workflow. So first, OBS Python, it's a Python library. Essentially, it loads and writes seismic data and applies poles and zeros instruments responses via time domain convolution. So this step filters the raw ground motion and signal through our virtual geophone. So next, Pyroco generates a fully synthetic seismic recordings for any specified earthquake source mechanism or subsurface velocity structure, giving us any reproducible like test signals. We then use the geophysical inversion and modeling library to confirm how seismic waves propagate through complex geological media by solving wave equations with finite element and special element techniques. So all these core calculations, including designing digital filters, computing fast Fourier transforms, and producing power spectral densities, are performed with numerical Python and scientific Python. Finally, we constructed an equivalent circuit model in SPICE, also standing for Simulation Program with Integrated Circuit Emphasis, to capture electrical details such as coil inductance and unintended resistance to ensure any simulated geophone responds like that matches the behavior of real hardware. Following that, so with our environment active, we upgrade the Python installer and pull in 5 key libraries. So as I mentioned, OBS Python for seismic data handling and instrument filtering, Pyroco for generating synthetic waveforms, the geophysical inversion and modeling library for finite element wave propagation checks, and number Python and scientific Python for all core numerical tasks, and lastly, matplotlib for plotting and data handling. So following that, we load and store these geophone instrument metadata to write a short script that reads manufacturer provided station XML files, which were downloaded from the data centers, and extract each geophone's poles and zeros description plus the sensitivity. We then dump this metadata into what's called JavaScript object notation, or JSON for short, file for easy reuse. So this is how our code knows exactly how a 4.5 hertz versus a 10 hertz geophone behaves. So next, we generate synthetic seismic signals using Pyroco's local engine. We define a simple one-layer Earth model and Ricker wavelet source. The engine computes what the ground motion would look like at a point 10 meters away. We write that result as a mini-seed file, the same format used by real seismometers. Next, we load both our synthetic waveform and our geophone metadata JSON, and we tell the OBS Python to apply the poles and zeros filter for, say, like the 4.5 hertz geophone. So the result is a new Mistry file that represents the voltage output we see in the field. So finally, we read the simulated output and remove any trends or edge artifacts and run a fast Fourier transform. So this would end up squaring the magnitude, which gives us the power spectral density. So we plot the PSD versus the frequency and mark the three strongest peaks. So these correspond to the geophone's resonant behaviors. And following that, we will also print out the dominant frequencies to the console. So following that, so on the left, figure 6 visualizes our semi-log plot, overlaying the simulation or simulated calibration curve, so which is in the blue, and versus a published reference, which is in orange. So the simulated model peaks at 9.2 hertz, while the published geophone specification lists 10 hertz, an 8% deviation, and the damping ratio matches exactly at 0.70, and the amplitude at resonance is within 7% of the published curve. So above evidence, both curves follow a 1 divided by frequency decay, confirming that the expected velocity meter behavior and these tight agreements within experimental variability demonstrate that our combined mechanical and circuit modeling are able to reproduce real geophone responses. So following that, on the right, figure 7 showcases the key metrics within the table. So it's just like the graph, but the simulated resonant frequency is 9.2 hertz, juxtaposed with the published data yielding 10 hertz with an 8% error, and where the simulated and published damping ratio contain a zeta equal to 0.70 with 0% error. And remember, there's no units for zeta. And the simulated amplitude at the baseline frequency yielded a negative 0.3 decibels versus the published data, which yielded a 0 decibel amplitude with a 7% error.
So I'm going to talk a bit about sort of some limitations of our model. So, like, yes, our model, it did perform well, but it does rest on sort of a few simplifications. We assume things such as linear constant damping, whereas real sensors exhibit nonlinear hysteresis and friction effects, especially at large amplitudes. Like those are pretty prevalent. At higher frequencies, coil inductance and skin effect losses introduce additional roll-off and phase shift that our simple resistor and inductor circuit emits. So that's just not really accounted for. We also have not modeled electrical and thermal noise sources, which set the sensor's practical detection limits. Looking forward, active damping circuits and digital inverse filtering can compensate for the low frequency roll off, and machine learning algorithms could flag anomalies in live data streams, improving both accuracy and reliability in the field. So, in summary, I'd say we've created a fully reproducible Python-based modeling suite that predicts geophone resonant behavior within 10% of published benchmarks. Its modular design accommodates traditional coils, MEMS, FBG, and force balance sensors by simply adjusting the baseline natural angular frequency and damping ratio. Next steps include incorporating nonlinear damping and noise floor modeling for enhanced realism, exploring graphics processing unit acceleration for real-time processing, and then finally integrating machine-based learning anomaly detection into our pipeline.
So this is our bibliography. Thank you. And special thanks to all all the mentors and mentorship we received.
I second that.
Brilliant. Thanks very much to the experimental and engineering team. That was very, very impressive. I'm blown away by the quality of that. So thanks very much, guys. I realized I probably should have said like, hi. I'm Toby. I'm the cosmology mentor, and this is if you didn't tell, this is the GSYP final day presentations that we're doing. So thanks everyone for being here, and I hope you've enjoyed the program, and I hope to see you all again in the future doing more awesome GSYP stuff, such as writing for the Starry Messenger, which you've already done because you all are going to show up in it. So next, who's up next? It is nuclear physics. If someone would like to share their screen, take it away.
So, hello everyone. This is nuclear physics. I'm Omar, and my presenter is Mingwei. Our mentor is Aurora Pinto, and we are doing nuclear physics. So, for our topic, we chose to research modeling neutron stars with a relativistic mean field approach. So, this is an outline for our research. And now let's get started. For the fundamental or basic stuff, we first want to know what are neutron stars. Neutron stars are just collapsed cores of massive stars after a supernova, specifically after type 2, because type 1a, b, and c does not produce a neutron star. And they are the most densest observable matter in the universe. So in the next slide, you can see a sphere here with a line in between. This line is the magnetic line of a neutron star. When this line here points towards us, towards Earth, our telescopes can observe the star. And when it's not, we can't see or observe or know where the neutron star is. There are some extreme properties of these kind of stars. Their mass is between 1.4 and 2.1 solar masses. Its radius is between 10 to 12 kilometers, and they are really dense. And the fun fact that in one of the films of Superman, he was not able to lift one spoon of neutron star matter. Even Batman built the key of his hiding place using matter from a neutron star to prevent anyone from holding it because it's very dense. So now our RF model wants to know how particles in the core of the neutron star work. So we have some rules to play with, like the mass. If our model predicts that the mass is more than the biggest star we know, or the star with the most weight, then it's not valid. Also, the radius. If our model predicted that the radius of the neutron star is more than 12 kilometer or less than 12 kilometer, then it's also not valid. Also, for something called tidal deformability, which is measured from the gravitational waves, and it quantifies or tells you how stiff the star is. Now, to go on to the model and get the derivation, everything with Mingwei, we should talk about relativity, the famous equation E equal mc squared, and quantum mechanics, the Pauli exclusion principle. In the core of neutron stars, particles are subjected to an immense pressure due to the density of the star. So it forces particles to be in the same place at the same quantum state at the same time, and cannot happen. So the Pauli exclusion principle tells you that when something like this happens, an outward force pushes the mass of or the pressure of the star itself back. So that's why neutron stars keep intact, unlike white dwarfs, for example. And also, we should know that these stars are overwhelmingly neutron rich. They have a lot of neutrons more than protons. So the nuclear force is sensitive to this imbalance, which must be accounted for. Now, to develop the model and know some derivations, I will hand up the mic to Mengwei.
So now that we've defined what we want our model to have, let's start thinking about what our model should look like. And so the first thought physicists might have is be using these fundamental theories because they're the most accurate. But a key problem arises is that the fundamental theory of the strong force, quantum thermodynamics, is non-perturbative and computationally unsolvable at neutron star densities. And so this means that we essentially cannot analytically solve it, which makes it very hard for us to computationally solve it, especially when you're considering a large body of mass. And so we have to resort to effective theories, which essentially encapsulate the key characteristics of the strong force, But instead of looking at quarks and gluons, it now looks at nucleons and mesons, which has the same overall effect, but won't have the intricacies. And so RMF is a very highly successful effective theory. And to understand why it's successful, let's think about what criteria we want in our model. As Omar said before, we want it to implement quantum mechanics, implement relativity, implement that isospin asymmetry, and also we need it to be analytically solvable, so it's not going to be very hard to solve. And so it does this, it implements quantum mechanics by treating nucleons, right? Because we're looking at nucleons, not quarks, as quantum ferromagnetic fields, obeying the Dirac equation. The intricacies are not important, but if you notice, they are fermions, which means that they will create that degenerate pressure due to the Pauli exclusion principle. We also have the fact that we're modeling the complex strong force using effective meson fields that mediate those interactions. And these two facts in tandem also mean that we are accounting for relativistic effects. This is because both of these are invariant under Lorentz transformations, which means that under the effects of special relativity, these quantities will remain the same no matter which perspective you'll take. So we are accounting for the relativity component. And finally, RMF theory applies some simplifications by using a mean field approximation, which is in its name, right? Relativistic mean field theory. And we can use this approximation because of the high densities. The neutron matter can be considered as a continuous medium rather than individual particles. So now let's think about how we're actually going to build this RMF model. In RMF models, we consider fields, and fields in physics are just regions of space with quantities associated with them. So for example, an electric field will have an electric vector associated with a point of space. And so our two fields we're looking at is our first, the nucleon field, which has a Dirac-Spinzer at each region of space, hence a Dirac-Spinzer field. And it represents the intrinsic properties of those nucleons, their mass, their spin, and their relativistic dynamics. We also have the meson field, which, as I said before, encapsulates the strong force and, attraction, repulsion, and the special forces created by the different compositions of neutrons and protons, because we have a dedicated meson for that. And these have different types. They're scalar, they're vector, and they're isovector, which is a special mathematical object. So what do we even do with these fields? Well, what we want to do is we want to define a Lagrangian density for these fields. And this is useful because it encapsulates the motion of the entire system. Now, this is similar to summing the forces in Newtonian mechanics. So in Lagrangian mechanics, we want to define our Lagrangian, the scalar quantity that encapsulates motion, and it's its kinetic minus the potential. And the reason we're looking at densities is because we're not looking at a specific particle in field theory, we're looking at regions of space. And so this density Lagrangian density is useful is because we can define action, which is S here, and that's equal to the space-time integral of the Lagrangian density. Now, space-time integral is just a fancy word of saying that your small changes, your dx, is instead a small piece of space-time, dt times dx, dy dz, right? And this action is useful because we can apply the principle of least action, which essentially says that a physical system will evolve in a sense that it will minimize the change in action. And so mathematically, we can represent as a small change in the action will be equal to 0, a small infinitesimal change in that action. And so if we combine equation 1 and 2 together, we'll get equation 3. And if you work through that integral through more, you'll derive the Euler-Lagrange equation for fields. And so this is essentially your Newton's second law for this field theory. And so as you can see, we have to take the derivative of each of our Lagrangian density with respect to a field, if you see this phi as a field. And so now we need to look at the specific Lagrangian density we are talking about. So here is the full Lagrangian density. It is a bit long, I will admit that, but we're going to break it down because the underlying complexities for each component is not important. What they represent is important. So when we're talking about free, the word free means that we're looking at the field independently. So the dynamics of the nucleon independently, the dynamics of the sigma meson, which is the scalar meson, which represents short range attraction, and et cetera, et cetera. And we also have 3 other terms. So the first 4 terms are the free ones, the fields by themselves. these ones are the meson fields interacting with your nucleon field. So the force is interacting with your nucleons. We have the scalar meson interacting with our nucleon field, which is our attraction, our repulsion, and our isospin, which remember is that force create that difference in strong force caused by the different composition of neutrons and protons. And we derive these constants for these interaction terms by just experiment. So that is a source of inaccuracy, plausibly. But when we sub that Lagrangian density into our Euler-Lagrange equation, we will get 4 field equations for each field. We've missed one out, but it's very similar form to the other 2 here. So this one's the nucleon equation of motion. This is the scalar meson, and etc., etc. And we want to solve these equations of motions to get an expression for the energy density and pressure, which will get us an equation of state, which is really useful to get the overall internal structure of the neutron star. The problem is that these equations are too hard to solve in the sense that they are actually impossible in general to solve, right? And this is because they have bilinear terms. If you see these psi bars times psi, and it makes it incredibly hard. So we need to reduce some of the variables. And so we use the mean field approximation, which was one of the great benefits of the mean field theory I mentioned before. And so we can replace it by the average value of each field's average value. So if you notice, the scalar meson at that specific point in position is now the scalar meson. That's because we can assume it's a uniform field because of this incredible density, which also means the derivatives vanish. And so now we can simplify this and solve a very simple, much more simpler equation to solve, which gets 2 expressions, as I talked about the equation of density, and they're really important to get the overall internal structure of the neutron star. And so I'm not going to go through all the mathematics, but this first term here of the energy density represents the kinetic energy of the nucleon itself. And if you notice, it has this m star, and so this is the effective mass. And so this incorporates relativistic effects, which is what we said before was really important for our model. And we have some other effects such as the attraction and the attraction energy density caused by attraction, repulsion, etc. In the pressure, we have a much more complicated term because remember we're talking about degeneracy pressure, and this first term represents that degeneracy pressure caused by quantum nucleons. And if you notice, it's negative against the attraction term here, which is quite interesting. But I just wanted to mention that. Anyway, so we can use this to model a neutron star, but we also must also enforce physical constraints based on actual empirical evidence and ensure that it solves beta equilibrium, which is how the star is stable, charge neutrality because mostly neutrons. And now I will pass on to Omar to see how well this equation of state did.
So if you look at this graph, also we will have some little rest of math. We will leave math behind now and look at this graph. There are 3 lines here, the red one, blue one, and green one. If our model predicted, which is the blue one, something in between the red and the green line, then we are okay and our model is valid. This line here is just an example. And if it goes beyond the red line or below the green line, then it means that our model is not valid anymore. Now, to bridge it, these field equations are not enough to bridge the gap to microscopic properties like the mass and radius we set as rules for the validity of the model. So if you applied Tolman, Oppenheimer, Volkov, TOV equations, we will get these 2 equations here. And if we chose a central energy density and then numerically integrated the TOV equations outwards from R0, and then when in the star surface R, the pressure drops to 0 because you're just at the surface now. And the star total mass is just m at m equal R in here in the equation. If we did that and repeated many times for many values of central energy density, then we were able to get the relation between the mass and the radius curve for the equation for our equations. And that's actually what we want. Now we will be able to see if our model is valid or not. And in the next slide, in this graph here, you will see that these are nicer J0740 or just some some just data from real world, from real neutron stars. And if our model is valid, then you will see that the MR relation or curve will be okay. So next one, we will talk about some limitations and uncertainties of the model itself, because the RMP model is an approximation with known limitations that we are going to discuss. There are theoretical uncertainties, which the first one is the mean field approximation. We ignore some quantum fluctuations and high order correlations, which may be important. That's actually why we were able to solve the super hard impossible equations, because we just got the average of them. And also the parameter dependence. The predictions depend on the chosen set of coupling constants, GI, and different parameter sets can give us different results. So we need to apply our model to a real thing, like real constants. Also, we didn't count what will later happen in the core of the neutron stars. Some weird matter like hadrons or quark matter may appear, and our model does not count for them. This one here shows if these matters appears in the neutron star, you will see the red line with this matter, and the blue line is nucleons only, which we applied our model to. You can see that the blue line goes through our test, but the red line don't. And this is example of what may happen if we use this model, because we didn't count stuff, so it may lead to a mess at the end. What we can improve is to go beyond the mean field approximation, which means to solve the impossible equations, and use more fundamental theories and just develop the Bayesian frameworks, combine different models, and systematically quantify theoretical uncertainties. And also we can do some observational prospects, like we can get more gravitational wave observatories that will provide extremely precise measurements of tidal deformability, maybe, or just future X-rays missions like the one before that will further constrain the MR curve, maybe get to get the bounds higher or lower than down, who knows. And now for the conclusion, I will hand the mic to Mingwei again.
So to wrap it up, we presented a model of neutron star matter using relativistic mean field theory. And we started from our fields, we derived the Lagrangian density, and then we derived an equation of state by applying the mean field approximation and enforcing some physical conditions. And then this equation of state is the key input for the TOV equations, which implement general relativistic effects, because our previous equation of state by itself was only including special relativity. And so it yields the macroscopic mass radius relation of a neutron star. And this framework was broadly successful. It produced models that are consistent with current observational constraints and was within the upper and lower bounds. But there are definitely significant uncertainties, and the most important of which is the true composition of matter at extreme density, because we are looking at a much more macroscopic, less fundamental scale because of some assumptions we've had to make. And so I hope through this presentation you've seen the ongoing synergy between astronomy for empirical evidence and very top-level nuclear theory, which promises an exciting future for solving one of the greatest puzzles in physics. Before we'd like to wrap it up, we'd like to acknowledge our mentor, Miss Aurora Pinto. You should see her on the Teams. And we'd also like to thank Alyssa and Rana for their contributions during the program sessions. Fun. Here's some references also.
Brilliant. Thanks very much, Nuclear Physics. Another amazing presentation. Super interesting stuff. Loving it so far. Everyone who's enjoying it, raise your hand. I don't know. I'm not very good at being an MC. All right, who's next? General. Let's have a look. Quantum physics. any quantum physicists in the room, in the house? Perhaps not.
Sorry, I'm just sharing my screen now.
Oh. Yes. This might not be the appropriate time to mention it, but I knew your brother, so there you go.
Can someone else share the presentation? It's not letting me.
There, I think I've given you some. Oh no, wait. What did I just do? No, never mind. I don't have the power to change that. Brilliant. Take it away, quantum mechanics.
Okay, so we were doing the applications of quantum tunneling, and our mentor is Arya Gonullu. I don't think she's here though. I'm not really sure why. Go to the next slide.
Arya's not well tonight, so she couldn't be with us, unfortunately.
Sorry, Ruben just said that his Wi-Fi cut out. So I'll take this bit. So just to introduce quantum tunneling first. So it's a consequence of the wave-particle duality, which is one of the main parts of quantum mechanics, where particles, instead of in the classical sense, if the particle doesn't have enough energy to go through a barrier, it can't and it never will. But because if we know because particles can act like waves, and if we know its energy, then we know less, that we have less, there's more uncertainty in its position, which is Heisenberg's uncertainty principle. And so if a particle is going towards a barrier, it can exist in a range of places, some of which is past the barrier, even if it doesn't have enough energy to surmount it in the classical sense. And yeah, as it says, the probability of tunneling can be expressed with this equation, where part of it is in relation to Schrodinger's equation, which is very important in quantum mechanics.
I can take over.
Oh yeah, go ahead.
So as you can see, the probability equation is the square root of that probability is a solution to a Schrodinger's equation. So another way of saying that is that the square of the wave function is the probability. And as you can see, mx, one thing as you can see, mx is defined by vx minus e, which is the particle's energy in the x-axis subtracted from its potential energy. And that's constant and negative, or constant and positive, depending on the state. Go to the next slide. The solutions to these equations are, depending on if mx is positive or negative, are traveling waves with phase constant k or minus k. So the sign of mx can be said to define the medium through which the wave propagates. It follows that the region of positive mx sandwiched between two regions of negative mx constitutes a potential barrier. This is because effectively a positive mx represents a scenario where the particle has less energy than the potential barrier, or in other words, it doesn't have enough energy to go around the barrier in a classical way. So the only way to go through it is to tunnel. So it's possible through this method that coupling occurs when a wave function impinges on a barrier that's thin enough. Oh my! As you can see in the diagram, some of the wave function, when it impinges on a barrier, can be transmitted to the other side of the barrier. There's a small probability that will be measured to be on the other side of the barrier to where it was originally found. The next slide.
Okay, so the first application to talk about is STM, or Scanning Tunneling Microscope. It is used to produce image to atomic resolution, basically relying on the relationship between tunneling probability and distance, which is the same formula we just looked at. Yeah, next slide, please. So this diagram shows the spatial relationship between the probe and the observed object. The probe has to be very sharp. The tip of the probe is usually made up of only one atom, as shown in the diagram. The distance between the object and the probe yields different tunneling current created by electrons tunneling from the observed atom to the probe's tip when a voltage is applied through the object. This means that by analyzing the current, the image is produced like a contour map. Next slide, please. To gain pictures of multiple atoms, the probe has to move across the space accurately. We made use of piezoelectric effect. Certain material produce voltage when deformed. On the other hand, by applying small voltage, we can get small deformation, which is also known as the inverse piezoelectric effect. So basically, that achieves the probe's movement through the 3D space. Next slide, please. So the advantage is that of the SCMs that the image is produced with atomic resolution, but the limitations are also obvious because the object has to be conductive. Also, if the object has a large work function, like diamond, which is shown on the graph as the red line, the tunneling probability would become negligible when work function is too low, or when a work function is too low, as shown on the diagram, the green line, which is zinc oxide, the change of the detected current against certain change of distance will be small, which is the steepness of the graph. So it is less sensitive and it produces low quality image. So this is apparently another factor that restricts SCM's practicality. Next slide.
So another application of quantum tunneling is in tunnel diodes, which are a unique type of diode, and they utilize quantum tunneling to produce an effect called kind of negative resistance. And to achieve this, they have an extremely narrow PN junction, which electrons can tunnel through. And the PN junction is where the two semiconducting sides of the diode meet within it. On the N side, there's the negative side, there's current flowing from the cathode, and material is doped to produce free-moving electrons, while the P side is doped to produce free-moving electron kind of holes. These kind of represent missing electrons in atoms and or other structures, and not actual particles, of course. These allow This allows current to flow in one direction in regular diodes because electrons come from one direction on the negative side and then fill the holes on the positive side. Can we go to the next slide? So the narrow PN junction of a tunnel diode allows these electrons to tunnel through it. So when in a forward bias operation, as the potential difference increases, the electrons can tunnel through and fill the valence states on the N side, and these align with the P side, where the holes are, and the current can then flow through the junction. As the voltage increases, though, the states misalign and the current again decreases, and this is known as negative resistance. This is a negative resistance differential, because as the voltage rises, the current drops, and this is the most useful aspect of a tunnel diode. And this is also good because above a certain threshold potential difference, they act like regular diodes again, and electrons can only cross the junction via conduction, not tunneling. Next slide. So as you can see in this graph, as opposed to a regular diode graph where it's all completely flat on the IV graph until a certain point where it increases extremely quickly, there is a kind of first peak that happens due to tunneling, and then another decrease because of the misalignment due to the increased potential difference, and then another increase when regular conduction takes over instead of tunneling. Next slide.
Yeah, so the next application was in nanocapacitors, which in where quantum tunneling is used. And so regular capacitors, to explain, are made from two electrodes, conductive electrodes, with an insulating dielectric in the middle, which is an insulating material that can be polarized, so it has high polarizability. So when electrons flow through the circuit, more electrons go into one of the electrodes, which polarizes the dielectric and gives it a positive and a negative side, which then repels electrons from the other electrode, which causes the flow through the circuit. And that charges the capacitor, so it stores energy in the form of charge, which can then be released as current when the voltage is removed. And this is being looked into and being researched quite a lot as a more environmentally friendly energy storage method, because it doesn't use any chemicals and it doesn't harm the environment as much as most systems that we use now. But it has quite low energy density, and so that's the main drawback. So nanocapacitors, which have a dielectric of only a few nanometers width, they have improved capacitance and energy density, so they're being looked into as a solution for energy storage. Next slide. Yeah, so where quantum tunneling could come in, which was the research that I looked into, used field emission tunneling, which is a specific type of quantum tunneling where strong electric fields are applied to a metal and electrons can tunnel through the surface of the metal and escape. And the probability of the electrons tunneling, it can be calculated, and it depends on the strength of the magnetic field and also the distance that it's tunneling. Yeah, so next slide. And that's used in nanocapacitors to increase the capacitance. And that was a recent piece of research that I looked into, where the field emission is used to allow electrons to escape from the electrodes, and they can then occupy electron holes in the dielectric in the middle. And when this only works when it's cooled to really cold temperatures. So it's here it was done at 77 Kelvin, where electrons can exist stably and the conductivity of the dielectric itself is negligible, and so electrons can stay injected into the dielectric. And you can see on the right a graph of energy density depending on the voltage which it's charged at. So at a certain voltage, which is where the peaks are, these are shown for two different materials. where the peaks are is where electrons can, the field is strong enough for electrons to tunnel into the dielectric from the electrodes, but only into the region around the electrode, which means there's a asymmetric charge distribution within the electrode, which means that once it's heated up and the conductivity is increased, then current can flow between the different sides of the dielectric. So it increases the energy density stored in the capacitor. And it can be, where in the research showed that it could be up to 7 times. The energy stored in the dielectric could be up to 7 times the energy stored in the kind of regular electrodes. And so it brought the energy density up to similar levels to the batteries that we use now, which could could be a major step in energy storage, but there are major drawbacks, like the fact that it has to be cooled to very low temperatures, so it still can't be really applied. Yeah.
Next, I'm going to talk about the next application, which is the tunnel field effect transistor. In fact, this is like kind of like a continuous application from the diode and also the nanocapacitance. So as you can tell, there are lots of transistors are widely used in integrated circuits, processors, and also graphic cards. So as you can tell, there are conventional MOSFET and also tunnel FET, which is the TFET and MOSFET. So as for the conventional MOSFET, which is widely used in the industry right now, it uses the thermionic emission, which the electrons must gain energy to cross the potential barrier. Where in the TFET, it uses band-to-band tunneling, which means the electrons just tunnel through a thin energy barrier without needing the electrons to possess energy that is greater than the energy barrier. So the key benefits here is the TFET can switch at voltages below the thermal limit of 60 millivolts per decade, enabling ultra low power operation. Let's begin with the structure of MOSFET. Yep, next slide. So a typical MOSFET consists of 3 main regions, which is the source, the drain, and also the gate, which are separated by a semiconducting channel, a thin layer of insulating oxide. Usually the silicon dioxide lies between the gate and also the channel. Now, on the other hand, let's look at the TFET. So TFET has a very similar looking structure to MOSFET, but with a key difference. The source region is made out of a P-type material, the channel is intrinsic, and also the drain is an N-type material. So it will form a PIN structure. Here, the gate will still control the channel through an outside layer, but the current flow mechanism is different. So next, I'm going to compare the current flow mechanism between the MOSFET and also TFET. So as for MOSFET, when a positive voltage is applied to gate, it creates an electric field that attracts the electrons into the channel. So it will form a conductive path from the source to the drain. Here, the electrons will flow only when they gain enough thermal energy to overcome the potential energy barrier in the channel. So this process is known as the thermionic emission. In conventional MOSFET, carriers must need to gain energy greater than the potential barrier to move from the source to drain. And this thermionic emission process relies heavily on thermal energy, and it also requires relatively high gate voltages. On the other hand, TFET, which uses the quantum tunneling concept, so when a positive gate voltage is applied on the TFET, it bends the energy band in such a way that the electrons can tunnel directly from the valence band of the p-type source to the conduction band of the channel, as you can see from the diagram below. This process is called the band-to-band tunneling, and it allows the TFET to turn on without needing high thermal energy, enabling operation at lower voltages and lower power. The barrier in TFET is thin and narrow, so it can allow electrons to tunnel through even with lower energy. Next slide. And last but not least, I'm going to talk about the advantages and also the limitations of TFET. So, as for the advantages, it consumes ultra low power supply, and also it could operate at a voltage that is lesser than 60 millivolt per decade switching, and it has low off current, hence less leakage, and promising for mobile and IoT application. And yeah, as for the limitation, it has low on current limits switching speed. And why there is low on current in TFET? This is because quantum tunneling is less efficient than thermal emission in this case, and it requires very narrow and well-aligned energy bands. So as for this case, this results in lower current when the device is on compared to a MOSFET. So, and the second limitation is the small tunneling distance requires precise fabrication. Fabrication. And last but not least, TFET is still under active research and development. Another thing, and I would like to add on is, the switching speed is related to how fast current can charge or discharge in the gate capacitance, which is mentioned previously by my peers. So in TFETs, because the on current is low, so it takes longer to charge and also discharge the capacitance. This slows down the transition between on and off states, hence limiting the switching speed. So I think that's all from our group, and thank you for listening.
All right, thanks very much to Quantum Mechanics Group. Another super awesome presentation, very sleek, very nice. Enjoyed it a lot. We've been going for about an hour here, so I think we're gonna take a small break. We'll be back here at about 21 minutes past. 21 minutes past with the math group. I think math is up next. Yep, math group. So feel free in the meantime to get your presentation ready and start streaming if you like, and then we'll be back 21 minutes past to resume. Yeah, see you in a minute. All right, and we're back. Somebody raise a hand if you can hear me. I probably should have paused the recording, but we'll just have to edit that out in post. All right, sweet. Time is 21 minutes past the hour. We're gonna resume with our mathematical physics group. Take it away, math team.
Okay, hi, I'm Kajol. I was the mentor for maths this year. I'm just going to introduce a bit about what we did as a group, and then some of our group will talk about their research. So to begin with, we talked about mechanics mainly and slightly more mathematical aspects. So we looked at Newtonian mechanics, Lagrangian mechanics, and Hamiltonian mechanics, and ways that they were similar and different. And this led us very nicely to Noether's theorem. So Emmy Noether, for those of you who don't know, is my personal inspiration in physics. But she was a brilliant German mathematician. She pioneered fields like algebra, abstract algebra, ring theory, algebraic topology, and in reference to physics, she made a huge contribution with Noether's theorem, which is used across all fields of physics. It's so fundamental. So Noether's theorem is all to do with conservation laws and symmetries. So a symmetry in physics is just a transformation that leaves the object or the system completely unchanged, so that's the same shape and the same size. And Noether's theorem states that if there is a symmetry, there's also a conservation law associated with this symmetry. So for example, translational symmetry. So if you move a system or an object, it implies that there is conservation of momentum. Rotational symmetry, so rotating, implies conservation of angular momentum, and time translational symmetry implies conservation of energy. And the idea of symmetries is very related to something called group theory. So group theory is related to like a set of numbers that has a binary operation, so something like addition or multiplication. And for this set to be a group, they must obey these 4 axioms. So that's closure, associativity, they must have an inverse, and they must have an identity element. So you can see this picture is just of the group of translations of a triangle, an equilateral triangle. So it has its identity element, it's closed. So applying each of these symmetries will give another element in the group. And there's an inverse, so you can undo these rotations or translation or reflections. And it's associative. That's given by the formula there. So if A is done to B first and then C, it's the same as if B and C are done and then A is done to those. The letters refer to translations. And for our project, we looked at specific type of group, and these are space groups. So space groups are the name given to a symmetry group of a collection of points. So we look specifically at lattices. So the symmetries of the space groups of lattices are the symmetries that the lattice obeys. So there's a few different types of space group, and they correspond to different translations, like groups that just contain certain translations, basically. And these may be reflections, rotations, things like that. And so for our research, each group member looked at a different type of lattice. So Iman and Ritaj were working on cubic groups. Simone was looking at the properties of space groups, and Eleanor's been doing a bit on hexagonal groups, so specifically things like graphite. And I will pass over to her now to tell you a bit about her research.
I wanted to first start by thanking Kajol for being such a great mentor. And I was, and I'm going to try and share my screen now. Oh, sorry, I was going to say, can everybody see my slides? I looked into the structure, symmetry, and space group, but specifically for graphite, since obviously we're the mathematical physics group, so the properties and implications it has. So I wanted to start off by talking about the basic properties of graphite, which a few of us might have already come across. So it has a layered carbon structure, so layers of carbon atoms bonded strongly within layers and with weak electrons between layers, and it has electrical conductivity, so graphite conducts electricity due to the mobility of electrons within its layers, and it has thermal stability and lubrication because it's thermally stable and it due to its layered structure, and I thought those diagrams were quite nice. So graphite's role in the industry. So graphite is used in a variety of technical fields, including batteries, graphene syntheses, refractory materials, nuclear materials, water purification, lubricants, and pencils. And this is an example of a battery, and this is an example of a refractory material. And here is a little pie chart from a different source, which shows specific percentages which is used in the industry. So one thing which I actually wanted to put on here as a clarification, since I don't take chemistry at a higher level, and I think this particular area of physics almost interlinks into chemistry, so I wanted to actually just specify the difference between a Pearson symbol and a space group, because these materials are essentially also classified with both the Pearson symbol as well as its space group, but they both serve separate purposes. So a Pearson symbol is a concise notation describing the crystal's lattice type and the number of atoms in the unit cell. So graphite is a HP4, so it's a hexagonal lattice with 4 atoms, and the space group is a detailed classification of the crystal symmetry operations. So the symmetry operations include translations, rotations, and reflections. And for graphite, it's P63 MMC. So it's number 194 in the directory. And here is a little photo of graphite as well as buckled graphite, which goes under this space group. And it indicates the hexagonal symmetry specific with glide planes and screw axes, which I'll be covering in a moment. So I just wanted to talk about what a symmetry group is, because one of the other members of our group who unfortunately can't make it today had a little bit about that. So I thought I'd also include that too. So symmetry groups consist of transformations preserving the structure of physical systems, so rotations, reflections. So they describe invariances in materials that influence physical properties and the behavior, and of course that's really important for its use in industry. So crystals have operations including, which we can see in the diagram here, including reflection, rotation, inversion, translation, and then the final part is glide planes and screw axes. So glide planes and screw axes. So the glide plane, so as an example is below, it's a symmetry operation combining reflection across a plane plus a translation parallel to that plane. So you reflect the structure, as you can see here, the first step across the axes, and then you shift it by some fraction of a lattice vector, so slightly up, so right here. And then a screw axis, which is above, it's a symmetry operation combining a rotation around an axis plus a translation along the axes. So you rotate the structure before sliding it down the axis by a fraction of the unit cell. So specifically for graphite, it will take quite a while to obviously, and I do not have the capabilities to describe this, but I just wanted to show how many sort of like small steps it would come to getting the full to making a glide plane of the full structure. But essentially, it's a mirrored plane perpendicular to the c-axis. So you basically get a c. You basically choose like an axis in the structure of graphite, and then that would be the c-axis, and then you reflect atoms across that plane before shifting them across the axis by half a unit cell. So it's basically reflecting and then translating it by half a unit cell. So that's how we use a glide plane for graphite. Whereas a screw axis for graphite, you rotate the structure by 60 degrees, and of course this is different for each space group, so that's why it's really important knowing the space group. So you rotate it around that same c-axis before translating it by half of the unit cell along the same axis, so rotating 6 degrees and translating by 1 half c. So I just wanted to say thank you to Kajol for being such an amazing mentor, and yeah, that's it from me. Basically only one of us could, so just me and Kajol for maths, but the rest of the group are going to have as part of the research page, so sorry if you're waiting for.
Oh, yeah, sorry, I thought there were more mathematicians to come. Sorry. Okay, great. Thanks, math. Sorry you have such reduced numbers. That's unfortunate, but there you go. Brilliant. I guess that's leaves us with our last but not least cosmology and general relativity group, which is my own. Whomever among you would like to stream. Looks like we have everyone, I think. Any cosmologists?
Mentors and helping.
Oh, sorry.
It's not like share the slide, but it's not. I mean, hang on. So yeah, we were looking at gravitational lensing. Very important in cosmology. We talked about his research. Just to check, can everybody see my screen? Can anyone hear me actually?
We can hear you now. We had a little bit of a problem before. I think your screen share. It just loaded. So there you go. But now we have it.
Oh, right. Oops. There you go. I'll reintroduce our project then. Annoying, it was working before. Anyway, so our group is doing gravitational lensing, which is very important in cosmology for various different reasons, which will be explained later on. But I'm going to hand over to Anthony to talk about his research.
All right. So to first introduce gravitational lensing, just a simple definition is when we're capturing images of very far away galaxies or stars, whenever there's a massive object which has a lot of mass and which causes a gravitational field, it distorts space-time, which actually causes the light rays to bend, and which is why we see these images to the left over here, where we can actually see that sometimes we can see multiple of the same galaxy or the same star. Next slide, please.
Oh, I'm good. Yeah, I would be able to. It would just be more convenient.
Sorry, technical difficulties. 1 second.
Anything okay, Cosmology group?
I think,
yeah, we're having trouble sharing right now.
Can everybody still see my screen?
Yes.
Oh, I thought I'd stopped screen sharing, but maybe it hasn't come through.
Let's see if I can change that. There we go.
All right. So moving on to my part of our research. So the first thing that I looked into was time delay, and time delay is basically where it actually takes longer for light to travel because of this large mass or gravitational field. And the time delay can be calculated with this equation down here. So it's called Shapiro time delay. And so it's 2gm, which is, the g is a gravitational constant. The m is the mass of this planet or star. The c cubed is the speed of light. And inside this natural log here, we have the radial distances from the receiver and the endpoint. And this is going to be important later on. And next slide, please. And so here's basically a visualization of what I mean by time delay. And you can see how the light actually has to curve in order to reach when we take pictures. All right, next. And another thing is gravitational time dilation, which is another phenomenon. And instead here, it causes time to slow down in regions of stronger gravity. And so if you imagine a bystander on a large mass, and we're visualizing a far away moving object, this phenomenon actually makes it so that time for the observer is slower than somewhere far away. And the Schwarzschild metric here is a complete solution for Einstein's field equations from his theory of general relativity. And we can manipulate it into this equation down here, which is d tau equals dt of the gravitational constant and the mass and radius. But besides that, from this we know that d tau is going to be smaller than dt, which means that time moves more slowly for the observer on that large mass. Next slide, please. And finally, on my end, I researched a little bit on Hubble's constant, and this can actually be derived from time delay that I talked about earlier. And so Hubble's constant is from Hubble's law, and it's the rate at which the universe is expanding. And so this constant can be calculated through many different ways. And one of these ways is from the time delay measure from gravitationally lensed images. And so this equation down here, delta t represents the time delay, and then d of delta t represents the distance of time delay. And again, c represents the speed of light. And all of this come together so we can get a relationship between Hubble's constant and this time delay time delay distance that we can calculate from our images. And I'll pass it on to
Oh, hi guys, I'm Elva. Just to check, can you hear me? Okay. I'm gonna talk about the deflection angle. So as Anthony explained, the gravitational lensing occurs when the light is bent by a massive object. So the deflection angle is just the angle by which the light is bent. Next slide, please. So here's a really mathy derivation of the formula. I'm only going to briefly talk about the maths. So the deflection, so the diagram on the top left is basically a light ray that's like approaching the mass and then it's bent. And we're just trying to work out the delta phi, which is like the deflection angle. And the d is the distance, it's the like y direction sort of distance between the mass and the light ray. And r is the radial distance. So we decided, we looked at the derivation in the Hartle's textbook, which was a textbook on general relativity. So following the derivation, we used the metric for black hole, and which is the really fancy stuff in the red like square. Because the metric describes the space-time, like the geometry of space-time around the black hole. So we can use it to describe the trajectory of light. And then it's just a bunch of algebra. I'm not going to talk about them in detail, but then we just arrive at the formula. The deflection angle is equal to 4 GM over c squared b, sorry, b, with b being the impact parameter, but we can prove that for a large distance, like if light is far enough away, then b would just approximate to d. So it's actually the distance between like the light source and the mass. Next slide. So something really interesting was that I believe it was Soldner, which is a German physicist, that basically he derived the first formula for the deflection angle, and then he said it's 2 GM over c squared b, which I think he derived it by assuming that light is a Newtonian particle traveling at the speed c. And then later, Einstein, with his theory of general relativity, derived that it's 4 GM. So this was like an inconsistency between the two theories. And later in, I believe it was 1919, the solar eclipse proved Einstein's prediction to be correct. So general relativity was more correct than the Newtonian theory. And then I'm going to talk about weak lensing specifically. So weak lensing by its name suggests that it's when the bending, so when the distortion is really small. And sometimes the lensing effect can be so great that it causes multiple images to form, or like there's going to be ox or Einstein's ring, which is called the strong lensing. Sorry, but weak lensing is more common. And so the leftmost image is a diagram of the weak lensing. So here we have the background galaxies, which are the galaxies in white, and then the foreground cluster of galaxies, so the black bit, and then it's marked in yellow. So the light from the background galaxies are going to be bent by the foreground galaxies to form an image on the rightmost panel. And you can see that they are distorted they seem to be stretched like tangentially around the clusters due to weak lensing. And if you look at each individual galaxy, the effect is so small that it's barely detectable by eye. So this means that we need to look at a large view of galaxies and use some statistical analysis to like better understand about the mass that's causing the distortions. Next slide, please. So here's an application of weak lensing analysis. It's the Euclid Space Telescope, which was launched in 2023. What it does is that it surveys billions of galaxies, and then it takes pictures of the distorted galaxies by weak lensing. So I think it's the image labeled A is a diagram of galaxies that are approximately the same distance from the observer, and the lines just show the distortions, so like shear transformations of the galaxies, and then astronomers can they can like analyze the image and then mark the because the Euclid Space Telescope, it only extracts the distortions caused by dark matter, which is something that you can't see but has mass. So in this way, we can construct a dark matter map that can basically show the distributions of dark matter in the universe. So I mean, this just helps. That just helps scientists understand more about dark matter physics and also the like cosmological model of the universe. So it's really helpful.
So onto the lens equation. This tells us how the apparent position of a source is distorted by the gravitational field of a lens. And these angles, these are all vector angles. So this beta here, I've included the latex form because I couldn't find the like the actual vector symbol. But this is the vector angle to the source when no lensing has occurred. But the theta is the vector angle assuming the lensing has occurred. And this vector alpha here is just another way of representing the deflection angle. So yeah, they're all the angles, but then the DLS, these distances here are not like absolute distances, they're just distances that the photon has traveled. So DLS is the distance from the lens to the source, and DS is the distance from the observer to the source. It's pretty easy. So next slide, please. Yeah, so this is just a diagram of the geometry of just like a basic lens. So as you can see, where this vector alpha is here, this is where we would see the lensed image. You can also see that theta is there. So that's just the angle that is subtended. And then you can see the source would be there, and then beta is the angle subtended, like we would see the source at angle beta if the source was not lensed. And then this equation is the Einstein angle. It just defines the maximum angular separation at which lensing occurs. So observationally, when theta is equal to the Einstein angle, the observer can see an Einstein ring. And that's very interesting, actually. It's just, you've probably seen lots of pictures of it. It's just like a lens, and then it's just a ring around it, really. So the Einstein angle equation is actually really, really useful in like deriving other forms of the lens equation, which we'll see later. So, well, later is now. So here is the derivation. So here is like a different form of the lens equation. So what we're doing here is we're just dividing this. In step one, we're just dividing the original equation by ds and then rearranging. So yeah, and then on the second step, we've got the what's it called? The deflection angle equation, which is equal to 4gm over c squared beta. But another equation is that beta is equal to theta dl. So we substituted that in there. And then in step 3, we're just showing this for the Einstein angle equation. So the Einstein angle would be equal to the root of that. So Einstein angle squared is equal to this expression. And in the 4th step, we are just substituting everything in, really. So all that's left is beta is equal to theta minus the Einstein angle squared over theta.
Okay, so now we're going to look at some concepts that are needed for some more detailed gravitational lensing. So firstly, surface mass density. So when we look out into the sky, what we see is a 2D image, not the entire 3D surface. So we imagine that if we put a grid on this image and then work out the mass per unit area, that is going to be our density. So what this first equation shows is we have we're integrating with respect to distance. So what we're doing is we're finding the total mass in columns extending from the observer to the source. Yeah, and so the second equation then takes concentric rings going outwards until we have a circle of radius b, which is the deflection angle. And so what we're doing is we're just taking into account all of the mass within the cylinder that we can see. And then if we plug that into the impact parameter and then we assume the mass is evenly distributed, we end up with this first equation. Sigma is the surface mass density. And then in the case where alpha equals theta, which is when beta equals 0, is when we have an Einstein ring, and we call this the critical surface mass density. And we can actually use this as a measure for convergence, and we call this ratio kappa. At the bottom, it looks like a K. When kappa is greater than 1, we end up with strong lensing. Kappa is less than 1, we end up with weak lensing and no image forms. And also, as briefly mentioned earlier, instead of just one image well, we always end up with 2 images forming in each plane of view if we have strong lensing occurring. Although if weak lensing occurs, we don't have an image. And also, the objects we look at aren't perfectly spherical with perfect mass distribution, so we're unlikely to see just 2 or a ring. Sometimes we might even see more. Yeah, so Fermat's theorem says that a ray of light takes the shortest path of least time, and then we can, using a form of time delay, we can take the gradient and set it equal to 0 to find all of the turning points, and this is where the images occurs. These extra images come in pairs, so we have an odd number of images, including the central one, so it kind of seems like an even number. And this particular example is called an Einstein cross. Then if we want to calculate the magnification and brightness, we can look at the ratio between theta and beta. So what we're doing here is we're imagining concentric rings going outwards from the center. And so we're building up that image. And so we have, in each ring has an area of 2 pi theta, which is the circumference, and then we're multiplying it by its thickness, d theta, and then dividing it by the equivalent for the original image. And so we end up with this expression where u is the ratio of beta to the Einstein radius. And so we end up with, and the top left expression is the magnification, or the extra bright, the magnification from each point source that we see, each theta, theta plus and theta minus. So when we add them together, we get the total magnification, see at the bottom. And then lensing potential is, it's a projection of gravitational potential onto the lens plane. It's useful for calculations. I think we define it as having its gradient equal to the reduced deflection angle alpha, which was mentioned before. This form of alpha wasn't shown, but it can be derived. And then using something called Poisson's equation for gravity. We can also show that the Laplacian of the potential is equal to twice the convergence. And this is going to be very useful later when we look at the Jacobian matrix. And one final thing with strong lensing. So far, we've sort of assumed that all of these distances are absolute, but they're not. The universe is expanding. When we're looking at these distances to galaxies, they're actually changing over time. And so we're going to look at co-moving distances, which are independent of the universe's expansion, rather than the difference between positions in space. And we're going to say A is a scale factor of how big the universe is at a given time compared to now. And we can write it in terms of Z, which is redshift. And so we're going to redefine ds and dl in terms of this scale factor times some co-moving distance using the Greek letter chi. And then we can represent it using these equations below, and the Hubble constant appears. And then we end up with, we can see that the Einstein radius will actually change over time. This is because whilst B, the impact parameter, is constant, the distance to the source will increase over time, although this will happen over an extremely long time. So whilst it can be used to find the Hubble constant, it's probably impractical. And also we can rewrite the time delay adjusted for the expansion of the universe too.
So in this section, we're going to go through microlensing. Next slide, please. So an introduction to microlensing is that it occurs because there is relative motion between the lens and the source. So it's not just static, well, relatively static objects. There is relative motion between the two objects, and the result is not a static image as before. It's a dynamic change in brightness. And we can use it to detect MACHOs, which stands for massive compact halo objects. They're actually dark matter candidates, and I've given a few examples on the slide. So there's the bell curve on the top left, which is a solution to Einstein's equation, and it's actually an exotic, like non-topological field. The bottom left is an exoplanet, specifically a brown dwarf called J1407b. It's a brown dwarf, so it has like quite high mass, and apart from gravitational lensing and maybe the transit method, it's very difficult to detect because it doesn't really emit its own light. And then in the kind of in central here is what I would like to say is a primordial black hole. Realistically, these things are impossible to see because they are very, very small, but their gravitational field is very strong, which is why we can detect them through gravitational lensing. Next slide, please. So this is just the mechanism for microlensing. The time taken for an object or a macho to move a distance subtended by the Einstein angle is equal to the time taken for the source to cross the Einstein radius, which is given by this formula here. And I've kind of included a animation here with a light curve at the bottom right. So this is how we detect like the machos. Next slide, please. Oh, actually, on the previous slide, there's an example of an Einstein ring, which is pretty cool. Okay, so critical and caustic curves. These are used a lot. Well, these are used mainly in microlensing, and critical curves are defined as like they just show where the image will be infinitely magnified, which is the graph on the top right. You can see the image positions here are just examples of like observational data, and the rings here are examples of where the image will be infinitely magnified. So caustic curves show where there will be multiple images from the same source. And you can see the same, there's a ring and then there's an odd diamond shaped thing. So in this example, there's an Einstein cross. As mentioned previously, there's only been 2 observations of these ever in the cosmos, so they're pretty special. And in this example, a quasar has been lensed so much by like a galaxy in the foreground that there's actually been 4 images, and that's what you can see here on the Corset curve, like these 4 peaks in the diamond. That's where the quasar is, like the lensed image. Okay, so the Jacobian matrix, this is relatively difficult. So it just relates the changes in the image plane to the source plane during lensing. But this helps to identify image deformations caused by the actual lensing. And there's different components of these, which we'll see in a minute. So next slide, please. So the derivation for this, so you have to identify the vector functions first, which we've seen previously from the lensing potential. And these are just the functions in the bottom left. But then you have to derive things. So you have to compute like a partial derivation with respect to different inputs. And these inputs are just the I and j coordinates from the source, which produces an output. And that's just, the output is just like what you observe is just the lensed image. And then just to get the matrix, you just assemble those derivatives. Next slide, please. So these are the geometric, these are like the geometric applications of the Jacobian matrix. And each component represents a geometric transformation. So the kappa, as said before, is convergence. It's just where it's either like a lensed image gets brighter or gets dimmer. The gamma, so you'll know what gamma is. A gamma represents a shear, which is basically just like, I think actually you'll know what a shear is, right? And then omega is a rotation. But normally we don't actually put omega into the Jacobian matrix because first of all, it becomes non-symmetric. And also physically, like realistically, in most cases, there is actually no rotation because the lensing potential tends to be scalar. Next slide, please. So more observationally, this is quite new. So in March 2024, JWST detected these things, LDRs. They stand for little red dots, and they're highly redshifted objects believed to harbor an active galactic nucleus. And there is quite a lot of evidence for this. In fact, there is extensive, but cosmologists think that LRDs only formed 600 million years after the Big Bang. And it sounds like a long time, but on the grand scheme of the universe, 600 million years is not that much. So when studying LRDs, we can get an idea of the conditions of the universe around this time. So whether it was hot, whether it was cold, like that kind of stuff. Next slide, please. So this is a very cool example given to me by Nikita. So this is Abel 2744QS01. So it was actually imaged first by the Hubble Space Telescope, HST, in shorter wavelengths. So you can see here 0.5 to 1.5 micrometers. And initially, because of this observation, it was just dismissed as like a high redshifted lensed object that was quite UV faint. And that's the UV on that. However, JWST resumed, like it kind of redid the observation in a longer wavelength. And what was discovered was it was very red, if that makes sense. So, which is quite like, it's quite shocking when you are observing things. So also something to point out is that we think it's an active galactic nucleus because Specifically, it has a full width, fully resolved hydrogen beta bar. So what that means is just the emission, which is unique to the accretion disk around active galactic nucleus, is the hydrogen beta. So yeah.
And again, we'd like to thank our mentors, Nikita and Toby, for supporting us and teaching us.
All right, thanks, Cosmology. I've suddenly become very dim. You guys were my main source of light. All right. Okay, thanks everyone for coming to the final day presentations. And thanks for joining us on the GSYP RMP 2025. Hope you had a great time, and I hope to see lots of you joining us again in the future on our various operations. Obviously the RMP next year, or contributing to the Starry Messenger, or any other awesome stuff that we do. I'd like to thank all the groups who presented. You guys had some amazing presentations. Really proud of the stuff you produced. I'd like to thank Arya, who isn't here. Unfortunately, she couldn't make it, but this is all obviously her brainchild, so we wouldn't be here without her. And thanks to the mentors for making it happen. Anything I'm forgetting? Maybe Pia, you'd like to add something? Or not? I think that's all. And we'll see you soon. Thanks, everyone. Good night.
Thanks. Bye.
Thank you. Sorry to put you on the spot there, but you know, you're like the second in command, so I thought you might want to add something.
Don't think of anything at the moment.
No, it's okay. I mean, I don't know, I'm just completely riffing. I probably should have, like, in the meantime, come up with something to say. Let me stop recording.
How did that feedback session